found your pizza and settled in. So this is the regular Monday image processing lunch, and a number of you are here for that reason, and that's great. And for those who don't know, come back any Monday, and there'll be presentations relevant to image analysis. Today we have a special speaker, and it's a special pleasure to have him here to visit. He was here for a conference over the weekend, and we mercilessly took advantage of that and asked him to come down and visit and give us a talk. Olaf Düssel is somebody I've known for many, many years. I think I remember at some conference years ago sitting on a bus with Olaf and discussing null spaces and inverse problems. And I think we bonded right away. And so Olaf comes from industry originally, worked for a number of years at Philips and then moved to academia, became the director of the Biomedical Research Institute at the Karlsruhe Institute of Technology, or the KIT as it's known. And I think the KIT sort of sees itself a bit of an MIT of Germany, and has similarly famous history, which Olaf explained to me when I visited with him a couple of years ago. So Olaf's background is very broad, and he could give many, many talks on a lot of different cardiac-related topics, and probably even some others outside of the heart. But we decided, again, because he was here for an AFib conference, and because atrial fibrillation is a big topic where a lot of us are involved in doing research on, that we'd have him talk on that today. So with no further ado, I'll pass on to Olaf.
Yes, thank you very much for the kind introduction, and it's a pleasure to be here again. I remember that also last year I was here. There I concentrated more on the inverse problem ideas, and today I suggested this modeling and biosignals, and this is not image processing. You will not find so much about this, but I hope you still will enjoy my talk. This is the team in Karlsruhe, and Gunnar here is fading out, let's say. He moved to Peter Kohl in Freiburg, but we still collaborate very intensively. And so I always have between 10 and 12 PhD students working in different areas of cardiac signals, inverse problem, cardiac modeling. And I like to say thank you to these guys. So this is a very crowded slide, and but I want to try to explain it because for me it's very important for understanding atrial signals, and let atrial signals guide you to diagnosis and therapy of atrial arrhythmias. We talk about arrhythmogenic substrates, and I would say every property of the tissue that is burned into the tissue for several hours, doesn't change immediately, and may lead to arrhythmias. That's what I mean here. And a substrate is something in the community which they talk about. We want to learn something about the substrate. There are areas in the tissue, might be areas where ectopic beats start. We have fibrotic tissues, very much discussed now, epi and endocardial dissociation. We will have lines of blocks or scars from former ablation. And also remodeled tissue is something that is at least burned into the tissue for several hours. On the other side, we talk about arrhythmogenic patterns, because as you may know, or I hope you know, there are depolarization waves moving across the tissue, and these depolarization waves might be either plane waves, I would call it. They are physiologic, they come from the sinus node and spread out across the atria in a regular way, and there are other patterns, circular patterns. You see, it's similar like this here, but here I mean the pattern, the circular pattern depolarization wave. We have breakthroughs from endo to epi, epi to endo. We have re-entries around obstacles, around the valves and so on. We have U-turns, rotors, and micro re-entries is a very, very important topic if you would have had the chance to go to Western AFib. Many, many talks are about rotors, and are they the most important part? Rotors is some pattern that is moving around like a rotor. Figure 8 re-entries, we also have wave breaks, wave collisions. And what we can measure in the end are arrhythmogenic signals with electrodes that we put into the heart. It is very common to put a catheter into the heart and measure with single channels and more with multi-channel devices. If you look at the electrogram of a single channel, you can find the activation time, when the depolarization wave is passing by, the duration of the activity, cycle lengths, and dominant frequencies. You find fractionated signals, low voltage signals, double potentials. And if you measure at many points simultaneously, you come to activation time maps. You can find the conduction velocity. You can find spatiotemporal recurrence of patterns. And if you then look at this, you find on this side people who want to discover AFib triggers, atrial fibrillation, some areas that trigger the fibrillation, and you want to find tissue properties that promote AFib. And on the other side, they talk about drivers and bystanders. You will find from cardiologists very often the word driver. They want to find the driver for AFib. No one has ever precisely defined what they mean with the driver, but let's keep it like that. It's something that, well, kind of drives the AFib. And the idea is if you wipe out this with an ablation, then the AFib stops. But if the driver is not in a region where the substrate is bad, then you might make a mistake, because you should always take care and try to ablate tissue that has some bad properties. And if you just wipe out the pattern, it is very likely that the next minute another pattern shows up. So if the rotors, they might anchor at fibrotic tissue, and they will often anchor at fibrotic tissue. So there is a link between the pattern and the tissue, but you might also find rotors in areas where the substrate is not changed at all. And if you then advise the cardiologist to go with the ablation to the rotor side, you wipe out healthy tissue. And that might not be the right idea, because if you wipe it out, the next minute another rotor shows up in a different area. You can do a lot here with late enhancement MRI. This is a specialty of Salt Lake City, the group of Nasir Marouche, together with you guys, several guys, I would say, sitting in the audience, trying to discover fibrotic tissue from late enhancement MRI, a very important topic. You can learn a lot about patterns from ECG imaging, measure the potentials on the body surface, and then try to solve the inverse problem. My personal point of view is that you will be able to find large patterns moving around the atria, for example, during atrial flutter, but you will never be able to see micro re-entries. This is not possible, and my opinion, everyone who promises that the machine they sell you, the ECG imaging machine, is able to discover several areas of micro re-entry, they are cheating. And what we definitely need in the end is the electrogram, because we measure directly inside the heart, and why we should always keep our objective in mind. Why do we do all this? We want to find a strategy that can solve the problem of the patient. That should be, it should not be just a mathematical exercise. It should always have this in mind. Now, this is was the introduction. This is the outline of my talk. You also again see quite a couple of topics. I will touch the challenges of atrial modeling, remodeling, drug effects, fibrosis. I will then go to electrograms. How do we measure electrograms? What is mapping? What do we measure with lasso, pentarray, basket, and high-density mapping systems? Then I will report about the modeling of important patterns and compare with clinical data. Then I'll talk about modeling of fibrosis and compare with clinical data. Then this rotor story, which is so important at the moment, and what do we see in clinical data. And I will end with the chapter, or a brief chapter on personalization of atrial tachycardias. Can we make a computer model of an individual patient? So I start with atrial modeling. From my point of view, these are the topics where the community is working on. We have to adapt cell models of the atria to heterogeneity, remodeling genetic diseases, influence of drugs, and sympathetic tonus. We have to then go to tissue and include fiber direction, personal anatomy, maybe pressure and flow into that organ model. We have to benchmark the cell models and the tissue models by comparing with others who do the same in the world. And we should definitely have more benchmark papers in this field. We have to include pathologies like scar tissue, fibrosis, endoepidissociation, hypertension. And we have to speed up. We need a faster calculation, and we have to find a good compromise with accuracy. And we would like to model ablation. The RF ablation, the cryoablation should be included into our computer models. And of course, it's trivial. You have always to be as close as possible to reality. And if you remember the last slide I showed you, then my plea is that the signals that you measure inside the heart, the electrograms, they are the direct view whether your computer model is on the right way. If you compare your computer model with late enhancement MRI or with ECG imaging, you are in a very indirect position, and you have very coarse data. And with the atrial signals, you have so detailed information about what's going on, so you should never leave that out. It's let's say, a little hint in the direction of Natalia Troyanova. If you look to her papers, she's excellent in combining late enhancement MR data and compares her results with ECG imaging results. But you very seldom see, and when you see only a few ECG signals. And I think this is a big mistake. Sorry. So this is about benchmarking. A paper that is in 2013. I just want to mention that there are different cell models of the atria. We compared these cell models, and we've compared how they behave on the long run and what might be the advantage and disadvantage of different cell models. We adapted the atrial model to different cell models for different tissue classes. The terminal crest has different tissue, is a different tissue class as compared to the pulmonary vein area and the septal area. You can do that. And this is the fiber direction. We started quite early with the rule-based system. This is here from 2011. And in the last 2 years, we have seen extremely interesting new data on the fiber direction in the atria measured with the CT and with diffusion tensor MRI and with the slices from donors from human hearts. So the knowledge is growing significantly in this field. Now this is about remodeling. Atrial cells change their electrophysiological properties if they go on for fibrillation for several months, and there are different ways to adapt the cell models to a remodeled cell. Axel Löwe in my group, he had a nice publication on the effect of drugs. He investigated amiodarone and dronedarone, very important drugs. In the literature, you find their effect on all the ion channels. You can include that for a normal concentration of the drug. But what he found out, what is nice and written down in this paper, during a day when you take the drug in the morning, then in the evening, the concentration goes down and goes up. And so he investigated these models of the atria and the arrhythmias and the antiarrhythmic effect in a broad range. And in that case, the old drug, amiodarone, showed up to be better than the new drug, dronedarone. That's maybe an interesting aspect. We always use 3D models. So this is all atrial tissue consisting out of, let's say, 1 million voxels, and we create a depolarization wave on one side, and then the wave moves through the tissue. And this is then an electrode that you can put into the tissue, and you can pick up the signals. And this is something that we do regularly to understand better the data that we measure and to compare with the computer models. Now I have 3 or even 4 slides on fibrotic tissue. I think this will also be in my conclusions, we are quite on the safe side in modeling healthy tissue. If we compare with the data that you measure in healthy tissue, it fits very nicely. The real problem is that there are patients on the table and they have some problems with their atria, and so the normal cell modeling doesn't work out properly. And the most important thing is fibrotic tissue, and there were several attempts to model fibrotic tissue. This was maybe one of the first ones, 2019, Vincent Jacquemet, who changed sodium channels and cell-to-cell coupling, and in particular, he introduced sets of collagenous septa disconnecting the transverse coupling. Then the group around Gernot Planck invented a method of node splitting so that you can also introduce layers in the tissue where the depolarization wave cannot pass by, and they are infinitesimally thin layers in between. Then there are a couple of publications from the group of Natalia Trajanova. The latest one here by Patrick Boyle, very, very interesting and important. She introduced, or they introduced here now, a kind of percolation. So they draw as if they put salt into the tissue. They put into that some fibrosis, some fibroblasts with different cell models and investigated this. I picked this as well because Frank is sitting in the audience. He was already 2099. He suggested better models for fibroblasts and a tridomain model, which is still an interesting aspect. Now, this is here a publication from the group here in Salt Lake City, and Christopher McGann, when he was still here working in this environment on fibrosis, and he compared with the histological slices, and the blue areas here are collagen, and you see how much collagen is in patients with severe atrial fibrillation. This is, I think, an important aspect. That led Edward Wigmont, who is now in Bordeaux, in the group of Michel Alsager, to introduce again a kind of percolation system, and they throw in randomly cells that just cannot depolarize. So they don't care about fibroblast models, they just throw in cells that are dead. And they get really data that are very similar in their simulations. They get data that are very similar to real electrograms, which is not the case with this here. So if you look at this signal, they claim in their conclusions that they get very nice signals that are very similar to measured electrograms, but I do not see this similarity. We have a close correlation with 3 groups of famous cardiologists, and we see electrograms every day, and they definitely do not look similar. This really looks like a signal that comes from fibrotic tissue. And then also here in the Western AFib workshop, we had the talk of Vadim Fedorov about the paper that they published in 2016. And they go with a microscopic view into that and find with an MR system with 80 micron resolution, 80 micron cubic voxels. So this cannot be done with humans. That can only be done with small probes or animals. And they discover these lines of fibrosis and dense fibrosis, areas of dense patches and lines of fibrosis in the tissue. And they also say that the breakthroughs are extremely important aspects of re-entries and initiation of fibrillation. This is the model that we use about fibrotic tissue. We also just throw in the voxels that cannot depolarize and then start again a depolarization wave. And this is a reasonable amount of fibrosis. That's a larger amount of fibrosis. And you see how the depolarization wave has to move through the tissue in a kind of zigzag pattern. The zigzag pattern is not only lateral, but also in the volume, up and down. That's why we think that for a good model of fibrosis, you need a 3D picture. Many others use just 2D pictures that will not give the right signals. And you can see this is the transmembrane voltage. Then you make a forward calculation and look at the extracellular potentials. And this potential you can pick up with an electrode. And what you can see first, it moves quite slow. It becomes larger and smaller. What you also see is this, I would call it jiggling, or what is the right word, forward and backward movement. And that will also lead to electrograms that are more and more fractionated and fragmented. So effective conduction velocity goes down and the signals become more fragmented. This is a signal in our computer simulations that you can measure if you increase the fibrosis. And what is also seen here, these are electrograms that you can see with electrodes with this very small distance. These electrodes only have 0.25 millimeter distance, and they look similar but not equal, because if you go onto fibrotic tissue, you will see a quite different pattern of the wave will go in a zigzag, and you will see that in the electrogram. So I definitely say that it is important to have a very dense sampling of electrograms and compare the neighboring electrodes, and this will tell you a lot about the degree of fibrosis and the type of fibrosis that you're talking about. Now I switch to the next chapter and look a bit into the electrograms and how we measure that. The conventional systems are here. This is a lasso with 10 electrodes and a pentarray, I think, with 20 electrodes. This A-focus with 20 electrodes. Then there is a large constellation basket. It has this size, and it can measure at many positions simultaneously inside the atria. And then this is a very new system from Boston Scientific called Orion within the arrhythmia system. The catheter is called Orion, and you see here many 64 electrodes that you can put into the atria. And this electrode is moving around and touching, sometimes here, sometimes there. And whenever they touch, they measure at 8 or 12 channels, really endocardial, beautiful signals. And that's really, we will see more data of that. This is how we observe what you see on the monitor. If you move around with the Orion in the heart, there's the catheter and the coronary sinus and an ablation catheter here. And what you see here is the result of 21,758 electrograms. They measure in 10 minutes to quarter of an hour 20,000 electrograms with beautiful signal quality. You can imagine how happy we are as engineers. These are data that we really love to have. So if we can then, what can we do with these data? It's the quantitative analysis of electrograms, and the topic is called then mapping. First, we have to remove ventricular far field. There are always signals from the ventricles, but that you're not interested in. And then, of course, everybody in the world does a local activation time and voltage map. How large is the signal? And these are things that we can do on top, and also other groups in the world are working on that. The RS ratio, the degree of fragmentation, the activity duration, the CAFE class. CAFE stands for complex fractionated atrial signals. And St. Jude has introduced a CAFE mean, and Biosense has introduced an ICL that's supposed to tell you something about the fractionation of the signals. Then there is a group here on cycle length, dominant frequency, phase singularity, and rotors. Here's a topic about entropy in the signal and recurrence rates. And finally, the conduction velocity. And I'm at the moment very excited about mapping of conduction velocity. That's why it was flashing a bit. I go through these things now step by step and look at patterns. And this is a very old movie that shows you a planar wave that moves across a lasso catheter. And if you then depict here the electrode number, there are 1, 2, 3, 4, 5. Here is 1, 2, 3, 4, 5, all the electrodes. And here's the time of arrival, the activation time. Then you will see the sinusoidal shape. And we published that already 2010. We find these shapes in real clinical signals. What you see here is the time, and here then the electrode number. And in the color code, we have the energy in the signal, we call it. It's a nonlinear energy operator that we apply on the electrograms. And these are real clinical electrograms. And where it is yellow, there is a strong activity passing by. And you see how a sequence of plane waves with this sinusoidal shape here is passing by. You can identify these signals very easily and find out the direction and the velocity of the wave based on these signals. This is another picture of the afocus. Of course, if you use an afocus catheter, you will have two sine waves here because you have an outer and an inner slope, but that's can be done. Then here we have an ectopic focus, and you can see that with this position of a lasso, the arrival time will be the same in all the electrodes, and here they will be different. You see again the sinusoidal shape. The bad news is that if the lasso is not right on the focus, you cannot distinguish the signal by no means from a plane wave. You have to move the lasso very near to the ectopic focus, then you can see this pattern. And we can really see this in real clinical electrograms. This is again a clinical measurement with our algorithm that identifies the activation. You see this shape, it looks a bit like a sine wave, but if you then make a local activation time map out of it, you see that it is a strong curvature. And so this pattern tells you that there must have been a focus somewhere here, and the wave, depolarization wave, was spreading out like that. So that works out fine. What we see in the hospital very often is lines of block. Either they have been created by an ablation procedure, but very often patients already come into the first ablation procedure with a line of block. And if you then switch on our computer simulation, you see how the wave goes around in a kind of U-turn. And this U-turn means that if your catheter is on this spot, you see a pattern like this. You have a large step in the activation time because the activation time has moved around here. And if your catheter is, or an electrode is right on the block line, you see double potentials. And this is a typical clinical example. There are two depolarization waves passing by in a distance of about 100 milliseconds, which is much too short as compared to the refractory period. And the reason is that there is a line of block in between these electrodes, which you can easily identify from these patterns here. Now, this is a computer simulation about fibrotic tissue. It's a wave that comes from left to right. We have already learned that the conduction velocity becomes small and the signal goes down in this area. And this is another explanation of that, which I skip. We have already seen the fractionation. I show this picture again because I want to show you how the signal becomes more and more fragmented in these areas. And this is what we see typically in the hospital. This is an atrium, and we have here a voltage map. And that means that, these areas here have a small voltage, and these areas here have a large voltage. In the areas of a large voltage, you see large signals, which have a beautiful, smooth slope. And in the areas of small signals, you see these fragmented signals. These are very typical shape of fragmented signals, and your computer models are only good, I would say, if they are able to reproduce this type of signal. And then I come to the last topic in this chapter on conduction velocity. We think conduction velocity is extremely interesting. It's the speed of the propagation of the depolarization wave. We have learned already it becomes smaller with a higher degree of fibrosis. It is low CV is pro-arrhythmic. The more areas you have with low conduction velocity, the more dangerous it is for the patient. They have high diagnostic value. But unfortunately, conduction velocity may be very heterogeneous. So not all the areas in the heart have the same conduction velocity, large differences. Conduction velocity is anisotropic. If you have a wave that comes from left to right, it has a different conduction velocity as if you look at the wave that comes from top to bottom. It will show change with cycle length, and it goes hand in hand with low voltage. And it can be easily determined in healthy atria if you have this nice slope of the depolarization wave. You can find precisely the activation time with an accuracy of 1 millisecond. And then if you know the distance between the electrodes, you can find the conduction velocity easily. But the patient has a problem. The patient has fibrosis. And then it is more and more difficult. And so it's really a challenge to make a good map of conduction velocity for real patient data. These are different ideas to measure the conduction velocity, and there was a very nice review article about that here, which I mentioned. And I don't go into the details of these methods. This is the cosine fit that I have introduced with the plane wave. You have finite difference techniques, polynomial fits, and the triangulation method. This is the one that we think at the moment is the best way. You have to have at least 3 electrodes, find the activation time in 3 electrodes, and then you can find the velocity and the direction of the depolarization wave from that. And this is now preliminary results, but I'm extremely excited. It is, I would say, the first time that you can see that because no one else in the world has done that yet. We take the data from the arrhythmia system, in this case, about 27,000 electrograms. What you see here is the activation time in the color code. You see there is something strange going on. This is an early activation, and red is a late activation, so there's moving something around here. And on top of that, you see the direction of the conduction velocity as a normalized arrow. So the arrows have always the same length, but they show you here what's going on. You see here very diffuse areas. In a small area, you find a large variation of the direction of the conduction velocity, whereas here you have a straight line where the depolarization wave goes down like that. This, I think, is interesting, and even more interesting is then, I would say, the speed, the absolute value of the conduction velocity in color code, in meter per second. So it's a quantitative picture you see here. And blue means the conduction velocity goes down to nearly 0. And red here is 1 meter per second, which is the normal way. There are different tissue classes and a small variation in this area. But let's say red is healthy tissue with a nice high-speed depolarization wave. And blue means a low conduction velocity. You could not see this line here in the activation time map because the depolarization wave was going from top to bottom. And that means that the activation time in this and this voxel is only a few milliseconds away from each other. You cannot see that in the activation time. But our algorithm takes the small distance into account and says that the electrodes have only a distance of 2 millimeters. And if then the activation time differs by, let's say, 5 milliseconds, you end up with a very slow conduction. And so you see features that you were not able to see with any other method. This is preliminary. What we did is we have a software package where we always click into these areas and see the electrogram, whether there were some crazy electrograms that you should have better kicked out. So we did that, and we see good electrograms here, of course, in this area, again, with small amplitudes and high fractionation. But we see good electrograms. We really believe that this picture is a right one. What we see in this patient is not a patch of fibrotic tissue. What we see in this picture is a line of fibrotic tissue, a line of block. And this is, I think, important. If I remind you of the pictures that you have seen when I started with the fibrosis and the pictures that come from the micro-MR system of Vadim Fedorov, he always found more lines of fibrotic tissue than just areas of fibrotic tissue. And patients are different. I hope that we are here able to differentiate between different types of patients, because if there would have been a large area of slow conduction, we would also be able to see that. In this particular patient, we have more lines of slow conduction, and this will have definitely a strong impact on the ablation strategy. You will have to treat this patient in a different way as compared to others. Now I'm talking about rotors here, and rotor, you can create rotors in a reasonably healthy tissue. So what we did in this tissue patch, we just switched on remodeling, but we did not throw into this any fibrosis, and you get a rotor. So the substrate in this area is not different from any other substrate around. If you give now the advice to ablate the rotor, you go into healthy tissue. It is in this case just by accident that the rotor was there, and the next minute it can be somewhere else. But we can find it with our classifiers, and what we see then is that in particular if you have this rotor, here the signal goes down to nearly zero. So in the tip of the rotor, you always have low voltage signals. And it goes down even to the so-called café class 3 to continuous activation. If you have continuous activation, I like to point out that it doesn't make sense to define a cycle length in this area. And if it doesn't make sense to define a cycle length, it also doesn't make sense to define a dominant frequency. And if you start an algorithm that you can find in somewhere, and they will give you some dominant frequency in this area, but it's rubbish. If you have continuous signal, you cannot, any number can come out there. So this is, I think, an important aspect to be careful also with these phase. If you identify the phase, then it may happen that you have signals like that, and then you can find the phase of the signal and make a phase map. And but you should always go trace back to the original signal. And if you start with the continuous signal, then the phase doesn't make any sense at all. And you should skip the idea of a phase map in that area. Now, the rotor means that if you go around that top point here, you get a 2 pi phase shift. And you can identify, you can find algorithms who identify these areas. Pavel Kuklik, who's now working in Hamburg, has published 2015 a nice paper where he find better methods and so on. And in the end, he said he just tried out to shuffle the phase. So he took the shape and made a random shuffle. And he could also identify rotors. So with these filtering methods that you need here, you can produce rotors out of random noise. So my message is, if there is a rotor in the atrium, you will find it this way, and you will get a spot, and the program will tell you at this point there was a rotor. But if you go the other way around, you look into the map of the phase map, and you think there was a rotor in the final map, you can never be sure that there was a real rotor in reality. You should go back and look into the original electrograms, because it might be that you have produced a rotor out of pure noise. So very careful concept. I think I skipped this one because of time. And we find these U-turns. We find very seldom, in our clinical partners, very seldom find rotors, although Sanjeev Narayan from Stanford says the rotors is the main problem, and you have to fight the rotors because nearly every patient has this problem with the rotors. Our patients are not as such. What we find quite often is this U-turn. This is really clinical signal and activation time, and you can see how the activation was moving around this. This is again a line of block, must be a line of block or an area of slow conduction, and the wave has to go around like that. If you increase the distance a bit from this picture, you could also easily say, oh, from my point of view, it's a rotor. So if you agree on that the term rotor is used for anything that goes around like this, then I agree. Then maybe the largest problem in the tissue of patients are rotors. But maybe for the ablation strategy, you should look a bit more in detail. And then you come up with this. Rotors very often anchor at fibrotic tissue. So we introduced into this here an area of fibrotic tissue. And if you then start a rotor somewhere, it moves around 3 times, 5 times, and then it locks into this area. And then you have, on top of the rotor tip, you have fibrotic tissue. And then you can see these type of signals that look very similar to the signals that we find in real clinical cases. And this is another simulation that the PhD guy, Marcus, started. He had this quite large patch here of fibrotic tissue. Forget the white here. This is just to guide your eye. It's just an area of fibrotic tissue. We now start, this is a healthy area, and we start, try to start a rotor with 2 stimuli, 1 wave and 1 stimulus here. But in healthy tissue, it wipes out. It is gone after a few turns. And here, the same stimulation protocol is started, and look what happens. It starts to move around, and it is from large distance. It is a rotating activity, and the reason is that we have slow conduction here, and this slow conduction reaches the outer end of the fibrotic tissue at a point where this is not refractory anymore. It can be stimulated. It starts a new wave here. And so it is a very good picture of what is observed in many clinical cases, that the boundary of the fibrotic tissue looks as if it's the most dangerous part, where the rotation is anchored and where the signals come from. I start now the same picture again, and I would like to guide your eye to this. We have rotating activity, and what happens now? 1, 2, 3. This looks like an ectopic center. So the same picture where you, on the first side, said it's a rotor, if you zoom in, then you would say, oh, there is an ectopic center. I would even claim, or guess, let's say I would guess, that most of the ectopic centers in the pulmonary veins, in fact, come from some fibrotic tissue in the pulmonary veins, and they are, in fact, micro-reentries. I don't believe that there are so many cells that start to depolarize spontaneously. I believe that there is a wave that is going down in a zigzag and comes out somewhere and leads to ectopic foci in the pulmonary veins. This is a clinical picture of our clinical partner, Amir Jadidi. And I have always to explain this picture a bit for those who are not familiar with it, because this, is it pink? This pink looks so dangerous, but it's in fact a healthy tissue. Somehow they have chosen this color. So this is healthy tissue, and here around, it's a voltage map. And here you have nice large voltages, and here you have small voltages. And from the electrograms of this lasso here, you can see that in the area of the healthy tissue, you have nice shape of the wave. And in this area, you have fractionated, fragmented shape. And you can also guess, estimate the conduction velocity. And you see that you have a very slow conduction velocity here and a large conduction velocity here. So they, in fact, observed here a micro reentry, or what say, is it micro? The lasso has 20 millimeter diameter. And you can compare that with our computer simulations and the signals and how they are fragmented in the You see in the fibrotic substrate and how they are slowed down in the fibrotic substrate. This all fits quite well. Now the last 3 slides, I think, about personalization of atrial tachycardia, I called it, because this was a case of atrial flutter, 70-year-old female, etc., etc. This is the activation time map, and you can switch it on. The color code is now moving onwards, but it's still an activation time map. And you can see that you have here an area of slow conduction that moves around, and it is based on, in this case, on 12,000 electrograms that they have sampled in about 7 or 8 minutes. And so we wanted to personalize the computer model of this lady that was in the cath lab. So we imported the data into MATLAB. We made a manual initialization of lines of blocks. So together with the cardiologist, we introduced some lines of block here. Then we estimated the conduction velocity. We have an optimization procedure so that we change the conduction velocity until the LAT, the local activation time, fits. And then we compare the result with the real data. And this is the output. So here we have the measured local activation time, and here we have the simulated local activation time. And this is then, well, these are again the measured data, and this is then the computer model of the atria. And I did not put them right on top of each other, but I tell you that these pictures of the spread of depolarization are very, very similar. So I think we are here on the right way of personalization of atrial tachycardia. So I summarize my talk. I told you in the beginning that for the physiological case, modeling and clinical data fits. It's quite okay. The challenge is now the realistic modeling of pathologies like atrial flutter and atrial fibrillation. What is the best model for fibrosis? I don't tell you that we have found the holy grail and we have the best model by just throwing in cells that we switch off. There are better ways, but it's an open question. It's an open question whether you need a fibroblast model. I'm more and more skeptic and say the fibroblasts don't change really anything. You don't see whether they are there or not. You have to introduce collagen and switch off the cells. There are also fatty areas in the tissue, and they are most important. But it's an open question. You have to identify lines of blocks. This is also very often omitted. You look into the pictures, and most of our patients in the first line have lines of blocks in their heart. And then, of course, you have to find the fibrotic areas together with late enhancement MRI. And you have to think about endo and epidissociation. And if we have done all that, of course, how can we guide the ablation? That is an open question that I leave for next talk, maybe next year. Thank you very much.